So welcome to Using Supercomputers Part 2. This glorious sunny day in Perth. Before I start the session and turn it over to our presenters, I'd just like to acknowledge the traditional owners and elders, past, present, and emerging, of the land of which we are presenting from, the Whadjuk people. I'd like to introduce our two lead presenters. If you can turn your videos on and give a bit of a wave, we've got Christian Di Pietro Antonio and Pascal Alahi. They are both Pawsey supercomputing specialists. In the chat answering questions will be Basha and Alexis. If you can pop your videos on, give a wave. So like I said, put any questions in the chat, and longer questions we will save to Q&A time. And without further ado, we've got a lot of interesting things to cover today. I will turn it over to Christian.
So again, welcome everyone to the second part of introducing supercomputing, where we teach you how to interact and to move the first steps into leveraging the huge computational resources that a supercomputer may offer to solve problems otherwise intractable. The objective of the course, comprising the first part presented last week and the second and last, is to teach you what supercomputers are, how to interact with them, and especially with the one we have at Pawsey. To do so, we require you to have at least a basic understanding of Linux, as most supercomputers use a Linux-based operative system. We also, in the previous part, last week, we have given an overview of a supercomputer, of its main components, both hardware and software, and how it differs from a workstation, in that many researchers are using it at the same time, so that resource access must be coordinated and monitored by the scheduler. Programs are not executed immediately, but must be submitted to a queue in order to wait for resources to become available. Today, we start speaking about storage. Storage is a location where data is stored, is saved, and programs can read from and write to. Storage in a supercomputer is subject to a lot of complex requirements. It has to be very fast because many programs launched from different users are executing at the same time and are using the storage at the same moment. It has to be available from all nodes, from all compute nodes that are many, so that distributed programs can read and write data easily. Finally, it must have a large capacity. Its implementation comprises several devices, several physical storage devices that are grouped together and managed by a software called distributed file system, which makes these devices available to all compute nodes and visible as a single logical unit. A node also may have a local storage that usually is faster to support fast computations. Here we give an example of such distributed file system, actually a partition of it, which is Scratch. We use it at Pawsey, and it is very large. It has 3 petabytes capacity. It is shared by all users, meaning that all users can see this partition and can write to a specific folder of it. Each user may create up to 1 million files. There is this limit, and it is meant to be temporary. Although it's persistent, meaning that if the file system goes down, your files will still be there, it is meant to be used for short term. Just the time to run your jobs and process your data. To enforce this policy, files that are not used for 30 days will be deleted automatically. Please don't rely on this feature to delete your files, but delete them as soon as you don't need them anymore. As I said, every user can access this partition, and in fact, there is a folder for each user under its group directory. So the directory tree starts with the Scratch, big Scratch folder. Then we have a folder for each project, and if you belong to one or more projects, you will have a folder which named after your username under each folder of a project, of the project you belong to. We define also the environment variable myScratch at login so that you can easily access that location. Now that we have spoken about storage, let's see how we can move data from your workstation to the supercomputer and vice versa. Transferring data between two computers over the network consumes computational resources of both. We don't want to waste computational time of compute nodes, and we don't want to disrupt connectivity by using login nodes. For this reason, we provide data mover nodes. Those are computers, nodes, that are dedicated to execute remote transferred programs, such as secure copy, for example. In practice, it means that you can use the host name of these nodes, which is hpcdata.pawsey.org.au, as part of the source or destination paths in the command line of your remote transfer tool. This transfer is initiated from your local workstation. It means that it can always reach Pawsey supercomputer because the Pawsey firewalls allow for incoming and outgoing SSH connection. This is not true for your home network or possibly your organizational network, which will block the incoming SSH connections. Let's see how actually this is done through this simple exercise. We will try to copy any file that you have on your workstation to your folder present on the supercomputer. As you can see from the slide, open your terminal. I will do with mine. We can try to do this together, but please try to do it also by yourself. I'm using Linux, so by default I have the scp command. But if you're using another operating system, for example Windows, especially Windows, you might have installed, as per instructions, mobxterm or filezilla to transfer files. So I give you 5 minutes to try this exercise. Just choose any file that you have on your computer and try to move it on your folder on supercomputer. As you can see on the slides, we have the path Scratch, which is common to every user. Then the project name must be substituted with courses 01, which is the project that has been created especially for this course. Username must be substituted by the username that you choose from the Google Docs.
So you can see me log in, so it's a simple enough change of command. And I'm going to copy, let's see, something not too long, but maybe quickly do something so you just kind of see, copy something. So in this case, and I mean, it doesn't matter. Okay. Let's see if I can type that right. Okay.
Be careful.
Well, you only can see at least one, but it's because I haven't hammered it, so I'm at least allowed to the right password? Just type it again. Let me actually look at it again.
Here's another one.
Oh, that's fine.
Perhaps this is a good point for Christian to go over again the password, like the importance of getting that password correct. I believe it's 3 times, correct?
And then it'll say permission denied, and then you can try logging in. But if you keep hammering the connection, it will eventually block you. So I've just copied some files.
Yes, exactly. And so I guess this makes the point that from this experience that some networks will block the connections from their side to Pawsey. So be aware that sometimes you have to ask permission from your organizational network to connect to external networks, I guess. But hopefully, Han will check the chat that everyone has managed to do some copy.
So I know individuals have logged on and worked on the supercomputers last week, most individuals here on the call. How are you going with doing this exercise? I know Christian had some issues with his laptop last week, and so that's on a different connection, which is blocking.
I think some people.
Okay, so we've had individuals who are able to do it. Perfect.
Okay, so we can probably.
We can go on.
Okay, so I will share again my screen. Sorry about that. Okay, share. Okay, another exercise is to back up your folder on the supercomputer. This is very important because Pawsey assumes that users are data aware, but will take care of managing the backup of the data. So through the same command, you can execute a backup by recursively copying all the content of your home of your group directory to your local file system. I guess you also can try this command. It's very similar to the previous one. Meanwhile, I give you 5 minutes. Meanwhile, I try to also solve my issue with the connection, probably.
Do you want me to do the command? Do you want me to do this? I can share if you want.
Yeah, definitely. Okay.
Okay. Let me center that a little bit so people can see it.
So we've got Pascal again sharing his screen and walking through the exercise.
Exactly. So I'm going to just copy back exactly what I've put in. I'm just going to seed into a temporary directory because I don't want to necessarily mess up stuff. And let's see. Do this. So this is going to recursively copy the directory into my local one, and just quickly here. So all right. Ooh. Oh, yes, of course. Okay. And it should copy everything back. You can see it copying. You can see the data rate's very high, but we're on the same network. So, and then if I obviously look locally, I can see the directory I copied, and everything's there.
Cool. So I can continue sharing my screen, and now we have seen how to initiate the transfer from our workstation. In some cases, it's useful that the supercomputer itself initiates the transfer, maybe automatically when possibly, or for example, after a job has completed. You can do so by submitting a transfer job, we can call it like this, through the copy queue partition. The copy queue partition will execute the job on the data transfers node so that the supercomputer will initiate the transfer to another location. As I previously said, it's very likely that your home network and your organizational network will block the SSH incoming connection. So make sure that you can reach the destination. Now, let's see what happens when we submit a job to a supercomputer. As soon as resources are available, the scheduler, in our case, in the Pawsey case is SLARM, will start executing your program on one or possibly more nodes, as depending on the configuration requested. Compute nodes are very similar to workstations, to high-end workstation, but they are connected together through high-speed interconnection. In this way, processes on different nodes can communicate almost instantly. Parallelism is when multiple processes on possibly different nodes work together to solve a problem. And it is the way a supercomputer must be used. Parallelism is not automatically achieved. Some packages, or the most popular packages, have these characteristics, this feature already programmed. But if you have a serial program that is a code that executes one instruction at a time, an expert is needed to revise the algorithm and its implementation. Yes. As an aside on parallel programming, we want to mention two fundamental protocols and their implementations, that is OpenMP and MPI. OpenMP is used to create threaded applications, meaning that an application with one process, but that process will create multiple threads that can take advantage of multiple cores present on a single node. On the other hand, MPI is a standard, and it has several implementations that allows several processes, possibly running on multiple nodes, to communicate among themselves using messages. MPI and OpenMP can be used in combination together to write distributed programs. We will not go further explaining about parallel programming because it's not the context of this course, but we have put this slide for you to go deeper on this topic. There are some references. Now that we are speaking about software, one might ask what is present on the supercomputer, what is installed. Well, of course, as a first item there is the operating system, which most likely will be a Linux-based one. Then we have compilers that are already present on the supercomputers. Compilers can be the most widely used ones, for example, GCC or CLAN, or specific ones, specific to the architecture that the supercomputer is using. For example, Magnus at Pawsey is a Cray supercomputer, and it comes with Cray compilers. Then we have debuggers and profilers to be used during development, as well as mathematical libraries that implement mathematical functions efficiently so that users don't have to. Of course, we have parallel programming libraries that we have mentioned just now, OpenMP and MPI, for example, to allow distributed programs to be executed and to take advantage of all resources. And lastly, the most widely used software packages can be found already installed. For example, VASP or OpenFOAM. But all this software is not all of this software is available or can be executed as soon as you log in. On a workstation, there is typically only one version of a software installed, so that the computer, in a certain sense, we can say that knows what to execute, or there is a graphical interface that helps the user deciding what to execute. On a supercomputer, we don't have a graphical interface, and typically there are many versions of a given software installed. To decide which installation of the software to execute, there is the module system. The module system allows for a specific installation of software to be used. Each software installation comes with a module, a so-called module, that when loaded, will make the installation visible to the user. The module command has sub-commands. Some of them are listed here in this table. For example, avail will show all the available modules. We use the term modules as also a synonym for installations, because there is a one-to-one correspondence between modules and softwares. List will list all the currently loaded modules, etc. Modules can also handle a combination of softwares. For example, if you're on a Cray supercomputer, you may not only want to use a Cray compiler, but also a profiler and debugger. And with only one module, you can load all these dependencies. This is used, for example, to define programming environments. For those who are more familiar with Linux, what module does is essentially modify environment variables such that they point to the correct paths for the selected software. And we have here an example. I managed to actually, can you see my screen, right? I can increase the zoom.
Another one.
Okay. So I managed to finally log in on the supercomputer. And we will try to execute these commands. The first one, let's see module list. Let's see what is currently loaded. So we can see that we have very few modules already loaded when you log in. We have Slarm, which is the scheduler and the system through which we can submit jobs. Then we have the architecture of the system, which is the module that defines some variables that will be used to, for example, during compilation, to optimize the process for this particular architecture. And we have GCC, a compiler. The first command, what we'll do, module, as the name says, we'll swap GCC compiler with the Intel one. Okay, so if you do again module list, you can see that we don't have anymore the GCC compiler, but we have the Intel one. We have basically said, okay, unload the GCC module and load the Intel one. Swap will implement these two operations with just one command. But what happens if we now try to load module load Gromax 2018? Okay, what happens is that module detects that there is some incompatibility between Gromax and the Intel compiler. This is because Gromax has been compiled with another compiler, probably GCC, but has not been compiled with Intel. So it cannot allow Gromax to be loaded, because if it does so, in future, further down the session, there could be some problem. So to prevent that, it blocks this loading command. On this slide, there are also other examples that I will not go through. Now, I think the first ones were quite explicative enough. You can have here some exercises that you can try yourself. I will give you a couple of minutes just to do some experiment with this module command. So log into the system and try these commands. Avail probably will show a lot of output because it will list all the modules that you can load, whereas list will only list the modules that you have that are currently loaded. What is essentially shows a description of a module. You can find useful information about the software, for example, with which compilers it has been compiled, and a brief description. We can go on and see how actually the scheduler, that is LARM, executes the program. With sbatch command that we have seen in the last week, in the previous session, we reserve resources, but those resources are not actually used, not until the program is actually executed. We execute a program, or the scheduler executes a program using the srun command. The srun command is put within a job script or used in the interactive session, and it accepts the same parameters or options that sbatch accepts. But at this time, you specify the actual resources that will be used. If you don't provide these options, they will be inherited from sbatch, from the environment that you define with sbatch. But it's also, I would suggest to specify them again, to not to rely on the default settings of the environment. So what sruns actually does is to launch the process, your program. We create a process out of your program on, depending on the configuration you specified, on one or more nodes. And we'll also decide how many cores per task and how many number of tasks you can create, and so on. You can actually go through all the options that srun offers through its man page or the web page of SLARM documentation, but it's not now this purpose of this presentation to go through all the options. But the most widely used one are essentially the one listed here. You decide the number of nodes on which the program will execute, the number of tasks that will be created, that is task processes, and the number of cores used on each process. As you can see, a program must be able to use those resources. So you have to write your programs such that it can be executed in a distributed environment. Otherwise, if you have a serial program, what happens is the same program will be executed multiple times without those processes to actually cooperate among themselves. We have to differentiate between different kinds of jobs that are executed on a supercomputer. Not always we need to execute a distributed program. Sometimes we need to execute a serial program, but that program requires an amount of resources, for example, memory or storage, that is too large to be found on a workstation. So you will have to use a supercomputer. Actually, at Pawsey we have a cluster that is called Zeus, and it's the one that we are using today, that is taught for executing serial jobs, jobs that don't use too many nodes. For serial jobs, you don't have to specify the number of tasks or the number of cores per task. It will, by default, it will use one core and will create one task. On the other hand, Magnus, the supercomputer that we have at Pawsey, and the difference between Magnus, a supercomputer, and Zeus, a cluster, is the interconnection between compute nodes. On Zeus, there is not a very powerful interconnection because nodes don't have to always communicate among each other. On Magnus, on the other hand, the interconnection is very powerful, and we would like people to take advantage of it. For this reason, Magnus is thought for executing very distributed programs, high parallel jobs that will make use of all the resources. Another difference is that on Magnus, you can allocate, the allocation granularity is per node, meaning that if you request one node, you will have to use all the resources on that node, all the cores. Even if you ask just one core, you will be given all the cores on that node. On the other hand, on Zeus, if you ask one core, you will be given one core, and the same node will be shared among different users. So please, if you have a serial code, run it on Zeus instead of Magnus. On Magnus, Magnus is meant to run high parallel jobs. Let's start with one example here. And the example shows a serial job, a serial script in Python that will essentially print an hello world string. What we see here is a batch script or a job script. And typically a job script is has several sections. You can identify the first one. The first one is comprises of several comments. Each comment, there are special comments that start with batch, and those comments define the resources to be allocated for the job. Those are directives that will be interpreted by this batch command, so that it knows what resources you need to run the job. In the second part, when the actual command starts, we will load typically all the software that is needed to execute your job. For example, in this case, the Python interpreter. Finally, we launch our job. In this case, we run the Python interpreter and give the script to execute to it, and we use srun. Note that not how srun is not given any parameters. It will inherit the ones specified in the batch directives, where we have said that we want to use just one node and create one task per node, so one task total, and one CPU per task, so one core. So it is really a serial program. Let's try to run it. So let's move on as you can see, I have already downloaded the repo. Let's move into the repo. Let's see what we have. This one is hello serial. Okay. So there are 3 files. We have hello serial py. If we do the cat, so showing the content, we see that there is only a simple print, and it will print an hello world string. Then we have 2 files, hello serial.slarm and hello serial.pbs. PBS is another scheduler used on supercomputers, but it is not present on at Pawsey. So we will use hello serial slarm. That is the scheduler used at Pawsey. Well, of course, right.
That's batch.
Yeah, no, but I just want to show the content first. Okay, so as you can see, it's the same one displayed on the slide. We have batch directives. Then we load the Python interpreter, because if we don't load the Python interpreter, it will not find the Python interpreter because it's not present on the default environment paths. Then we run the job. You notice that srun is missing here. It's not a problem because being a serial job, if you execute the program without srun, it's fine. It will execute the program without using multiple processes or without using multiple cores. srun is useful when you want to specify how many nodes you want to use, how many cores, how many tasks in this kind of distributed environment. But in this case, it's enough to specify just run the program as usually you would do in your own workstation. So to execute this program, simply type batch and this JavaScript, which is hello serial.slar. As you can see, if the command is successful, it will show you that it has been submitted, the job, a batch job, and it will give you the ID of the job. If you type sq --me, it will show all the jobs executing. But since this one was very fast, you cannot see in this list. But if you type ls, you will see that there is a new file called slarm dash the ID of the job. If we use more, the command more, to see what's the content of that file, we see the hello world string being printed. So what is this file? This file essentially, all the output, the normal output or errors will be redirected to this file so that you can check the output of your program later. Okay, this was a serial example. We can go further and try a more advanced one. Advanced in the sense that we, at this time, will use the OpenMP framework, the one that I briefly talked about previously. And this program will create a single process, but that process will create multiple threads. In this example, 28 threads, one for each core available on a Zeus node. The first part of the script is essentially similar to the last one, except for the fact that we request now a core for each thread. So we specify CPUs per task, 28. So 28 CPUs per process. Then the second part, in the second section, we see that we set some variables, environment variables, that are used by the OpenMP framework. What essentially we say is that we say to OpenMP to use 28 threads and to bind each thread to a core, to a different core. Then we finally launch our program. This time we will use srun. We need to use srun because at this point we want to specify how many cores we want to use, which is not just one, but 28. This is a C program. So let's go, I go back to my terminal. So this C program is not interpreted, must be compiled. So cd hello OpenMP, and we see that there is no executable. We need to compile. So let's compile with make -f, and we specify the make file. GCC. We have a makefile for different compilers. Let's just use the GCC one. Okay, looks like it has compiled. And we have the LOpenMP GCC executable. Now we can batch. We can do as previously. We use sbatch to submit the job script to the scheduler. So hello OpenMP GCC.slar. I guess maybe we can ask if there are some questions at this point. No? Okay. So let's see. Okay, there is an output file. Let's see what is the output. Okay, as you can see, well, the program consisted of a similar print process. It will print at each thread, will print its ID and on which processor it's running. As you can see, the output file now consists of several lines. and there is a line for each thread that has been created. Each thread will print a line that shows its ID and the processor it's running on. So yeah, there is also a print that shows that there are 28 threads in total. Another fact that we can notice from this is that you have multiple threads running, in this case a single process, but in the case you have multiple processes also, all the output will be redirected to this single file. So you can find all the output, unless otherwise stated with some special option, all the output will be collected on this file, this larm-id.out. So just for the sake of completeness, let's try to, I would say, remove the executable and submit again the job. It should give some error because it cannot find executable. So we have seen that the job has been submitted, okay? But at this point, if we do more slarm, the ID is 17, okay. Okay, we can see that also the error is redirected to this file, and there is this error that says srun cannot find the executable lopenp gcc. This is because it is not present on the folder. I guess hopefully you can follow with me and try to practice these examples, but you will find the slides also will be distributed later so you can try on your own time. The last example is the one using MPI. So at this point, we not only will not create a single process, but we will create multiple processes. Multiple processes. So as you can see, instead of as you can see, instead of having CPUs per task equal 28, so 28 cores, we will have tasks per node 28. And so we will create 28 tasks, and each task will have one CPU, but we will have 28 tasks. So in total, we will use 28 CPUs, one CPUs per process. The command at this point, we see that we need to load OpenMPI. We need to load OpenMPI so that the program, the executable, can find the libraries needed for MPI to work. srun is also needed so that 28 tasks will be executed. And finally, the last parameter of srun is the name of the executable, this point, LOMPI. Again, we need to compile the software. Oops, move again. LOMPI. Make, of course, there is this error because I've typed make, but what it says, MPI CC not found. It cannot find the compiler for MPI. This is because we didn't load the OpenMPI module. So module OpenMPI, a module load OpenMPI. Okay, now if we type make, hopefully we compile, and it compiled. We have the executable now, hello MPI, and we can submit the job. Batch, same way. Once you have the script, you can submit the script in the same way, hello MPI slar. Okay. Okay. We have the output here, and we can see that it also produces the due output, which prints the ID of the process and hello world. It's just a simple output. Lastly, we have a very simple exercise. We ask you to to follow my steps and execute the serial job, which is, I guess, the Python one. So try it yourself, or even try to execute the other ones and see if you can manage to do it or you have some error. Hopefully everyone has managed to do it. And last topic that we'll speak about are interactive jobs. So far we have submitted jobs to the scheduler so that it will execute them whenever possible, when resources are available. Sometimes if you have to execute a not so big job that does not require a substantial amount of resources, you can try to execute an interactive job, meaning that if available, you can access resources interactively. In practice, means that you will have a command line, a terminal access to one or more compute nodes. This is possible when you request not so many resources, so that the scheduler will readily find some resources to give to you. We do so by using the salloc command, which is the companion command of sbatch. Salloc will essentially takes the same parameters that sbatch takes. So you specify the number of tasks, the number of nodes you require, and the time limit, the maximum time your job or session will run. But instead of executing a program in a batch mode, it will give you access to those resources in an interactive way. This is useful, for example, for pre-processing or post-processing, or even more so for compiling and debugging your programs. So let's do it. Let's just give an example. So far, for example, this Hello MPI, this example that you can see here, we have compiled it on the login node. Now, this is a small program, and it is fine for our training purpose. We didn't use too many resources. But if you have a big program and you would like to experiment with the compilation process, it's very important that you do so on compute nodes. But on the other hand, you don't want to write a bad job, because there could be errors coming up and you want to quickly investigate them. To do so, you can request an interactive sessions on the compute nodes, essentially. You do so by using the salloc command. So we have salloc. For this training, you have to specify a reservation, but it's not even necessary to do so. But if you don't do so, reservation, you have to wait that general resources will be available. But we have some resources that have been allocated just for us. So let's use the reservation, which is course queue. Okay. Then we require one node, for example, and we say that we want to execute, for example, 28 tasks. Let's see, 28 tasks. We have to specify our account, which is courses 01, and the last needed parameter is in which partition we want to execute our program. Typically for this reservation, I think we have only work queue, right? But to debug and compilation, you could also use the debug queue. But for now, let's use the partition equal work queue. Let's see. A recognized option, meaning that I did some spelling right. Partition. Okay. You can see that it says that I've been granted the allocation, and it was waiting for resources configuration, meaning that if those resources were not available, you were left there waiting until resources become available. But now we have those resources, and it says nodes Z043, since we have requested one node, only one node, that node is available ready for the job. And as you can see from the prompt here, we are now no more on the login node, but we are on the compute node. If we have requested more than one node, still we would be on a single compute node, but we would have at our disposal more nodes, and you could use more nodes by executing the srun command. So let's see, srun n1 tasks of LOMPI. Let's see if it works. So what we have done, we have said we have created, we have requested 28 the possibility of executing 28 tasks, but srun we just specified one. But at this point we can change this parameter, for example 5, and 5 processes would be created up to 28. Okay. But what happens, for example, if we try with 29? It says unable to create step job for, it's unable to execute this command essentially. This is because we have requested more processors than permitted. Okay. As final, of course, you can execute the compilation of the software. Okay. So with this, you may try to also execute, or I give you a couple of minutes to execute the serial script in a Salok session. I guess you can start to come here, Pascal. Yeah. Thank you, everyone.
Thank you, Christian. And while we're doing a bit of a swap over, there's one question. So does n task refer to the number of threads?
So, sorry.
Yeah, go ahead.
N tasks refer to the number of processes of the overall computation.
Yeah.
Then you can also distribute, you can also assign a certain number of processes per node with the option n tasks per node, I believe, yeah. But it refers to the number of processes, not the number of threads.
So you can have a process spawn many threads, right? The idea is that you can have the parallel architecture such that you say, I want one node, I want one task per node, but that task is allowed to spawn n number of threads, or you could have a distributed set of computing.
So I think that what we can say is that srun, which is essentially, you can see that as a wrapper around MPI execute, MPI exec, will only manage the creation of processes.
Yeah.
And it can allocate a certain number of cores to each process, but then it's up to the program to use those cores. And you can do so by using also OpenMP, but you have to program your code to use those cores to create threads. So MPI or srun will create the number of processes, but then you have to create the number of threads for each process if you want to. Yeah. I cannot hear the answer, but okay, I will have.
Okay, so I hope that answered yes, that answered the question. Thank you. And over to you, Pascal.
All right, so I'm going to take the presentation in a slightly different direction and get you guys to think about essentially your problems, the research you want to do, the science you want to do, and how an actual HPC machine can, fulfill the ideas you want to get, like improve your science. And in part, it's important to think of what an actual real world use case would be in a real world HPC. So of course, what do you want to do? Usually you want to get the answers that you're trying to do for your research or any particular project as fast as possible. If it takes 2 seconds, that's perfect, right? You want to minimize that time. that wall time, right? The physical amount of time it takes to do something. But there are questions of how you get there, right? So if you think of a problem that you're going to try to solve, you have computing resources you want to use, and you want to try to tackle it efficiently as well. And you need to think of the cost, right? So if you had an infinite set of resources to solve the problem you had in an infinitesimal amount of time, that might normally be great, except it might not be efficient. It might be that you want to take a little less computing resources, take a little longer, and get an efficient computing outcome. Because you want to do it efficiently and you want to get it as fast as possible. So there's these ideas to think of when you're actually doing your programming. When you eventually start running problems at very large scale, you can't necessarily ask for the entire supercomputer to try to get the answer in 2 seconds. You might have to wait 20 hours and ask for small portions of the computer. And an example of the cost to think of, right, is if you had 12 hours and you're using 100 nodes of a supercomputer, and each node had normally n number of cores. In Magnus, it's 24. And a bunch of machines, it can vary quite wildly. But let's say you had n number of cores. You're using quite a lot of CPU hours to get an answer. And you want to find the best possible sort of a compromise from getting the answer as fast as you can, wall time wise, and using reasonable amounts of computing resources. The other thing that you have to think of is, of course, for everybody who's maybe doing software development or even using codes that are already parallelized, is what can be done. So not all problems can be tackled in a simple parallel fashion. If you had to step through something where you had to know what the last element was of the last compute, of course, it's kind of a serial type of process, right? You're computing something serially. You could try to do that problem in a different fashion parallel-wise, but it's something to think about. Because some compute can be done easily by distributing portions of a problem. If you had, let's say, a mesh, a grid, two-dimensional grid, and you want to split up, you could solve portions of the grid separately from other portions of the grid. So it's kind of a way of thinking about how you start parallelizing this problem, or how possibly the codes you use also parallelize this problem, right? If you're doing development or even use, it's good to understand how it goes about trying to do stuff in parallel using a supercomputer. Some problems are tackled best with CPUs. So if you had a machine that had 10,000 GPUs, graphical processing units, but the problem you have that are trying to solve does not suit that type of resources, you can't really use that resource. It makes it difficult. You have to think about these things. Some are very efficient at running GPUs. So if you had floating point operations, if you were looking at, I have a problem and I want to multiply a vector by another vector in solving my larger problem, that's pretty good for GPU use because you're just multiplying stuff. If it's far more complex, you might have to do something a little more interesting to try to figure out how to parallelize your problem. And it's kind of a useful use case to kind of think about. There are, of course, embarrassingly parallel problems in the sense that you are essentially running almost a serial task, but you're running many of them. So they don't really need to communicate. You don't have to really think about how things are managed. And the reason I'm going to mention that in a little bit is a particular use case that's really interesting. But it's important to think that when you're sort of thinking of these problems and how to go about solving it, that a real-world HPC system is not essentially an infinite block of CPUs with an infinite block of memory. There are discrete elements. This was mentioned in the first problem. It's important to think about. You have essentially a smallest compute resource, right? It essentially is a motherboard, a blade, a node, where you have a node where you have a couple of GPUs, maybe a couple of CPUs. They have memory that they can share, they can transfer information, right, between CPUs and GPUs and GPUs and CPUs, and then CPUs from one node to another, right? And an HPC system has this essentially compute element, right? And that is connected to other compute elements, other nodes with a very fast interconnect, a way of transferring information quickly. Right? So there are memory limitations per node, right? And an individual CPU does not have access to all the memory of, let's say, Magnus. That CPU could not necessarily immediately, trivially access all that memory. You have to think about how it would access all that memory. You'd have to talk to something that's managing that memory. It doesn't just have an immediate, you can't just go, I want to allocate something that's enormous, right? So there's limitations per node. There's limitations in the total memory, which is kind of obvious. There's also something subtle if you were thinking about really complex, really big problems. There could be some issues where you were like, oh, it's not going as fast as I thought it would. And that could be literally you have to communicate. There's some latency between communicating between one thing that's doing some bit of some task and another computing element that's maybe on another node at the other end of the machine. if the topology is not necessarily perfect. But anyway, the idea is that there are limitations. You can't just assume that things will scale perfectly and that you can use everything in terms of the resources. There are memory limitations, and there's obviously also electrical limitations and heating issues. You can't necessarily use, specifically in the largest machines, some of them just literally can't power the entire machine continuously for days at a stretch. They will use portions of the machine to go up and down. It's very subtle things, but it's something to think about if you're going to crazy scales. So the idea is to think of that the HPC system is not a single computer with just a lot more resources, and that you can just have a program that runs on a workstation that trivially then goes to scale on a supercomputer, right? The simple things like you couldn't build a motherboard that would be big enough to actually have just one continuous block of RAM, have it cool and powered effectively. It's not possible. But there's also a subtle thing is that obviously if you're building a supercomputer, you want multiple users to use that resource. And so you would normally have a very difficult time trying to share a resource if it was literally one block of CPUs and memory, right? It's not that possible. And so the software that runs on these machines has to account for the fact that you have resources that are distributed, and you have to figure out how you access these resources. Now, one of the ways that around this is this embarrassing parallel problem. And I thought this would be an interesting case for a lot of people to maybe who are not necessarily knowing the details of this. So obviously from COVID research, there's a lot of people wanting to participate. And one of the ways to participate in some of the research is a software program called Folding at Home, which is essentially just protein folding. And all it does is protein folding. But the way it does this type of protein folding is very asynchronous. You basically have effectively the ability to use the internet and all computers connected to the internet as if it's normally sort of like an HPC machine, because you give it's an embarrassing parallel problem. Essentially, the server gives a little packet of data to a computer, says, go check this protein, see how it folds, and return reduced data products. So that computer doesn't need to communicate to anything else while it's doing any computing. It just does its processing. And the reason this is kind of interesting is that Folding at Home, at least nominally for quite a while, is the largest functioning HPC machine in the world, in the sense that it has access to lots of resources. This is not a real HPC machine because it's a very particular problem, but you can look at how many CPUs were being used by this bit of software, and it's in around 3 million CPUs or 21 million cores, and it's going at exascale computing. So the future of supercomputing, everybody who are running really large machines want to hit exascale computing, which is 1 million trillion flops per second, or floating point operations per second. And this program, just because of the way it's kind of oriented and how it's doing and how it can distribute tasks to computing, was hitting close to that target. It was hitting around 800,000 trillion floating point operations per second, which is more than the current top HPC machine by just a little bit. I mean, the big HPC machines are still there. And it also is kind of equivalent to the biggest HPC machines in just a number of computing resources. But it's a very special case, right? In this case, it's kind of like running a bunch of serial programs that don't have to think about how they parallelize anything. It's just sending small data products and they can use the internet. And that's not what you're going to be aiming for when you're using an HPC machine. An example of a real, let's say, more grounded, but slightly harder to wrap your head around example is NWChem, which is an open source, high performance computational chemistry bit of software. It is normally meant to look at the interactions of molecules and nanostructures, so it can look at quite large structures. Nanostructures, it's meant to go from the quantum regime to the classical regime and look at how various substances interact, right? And this is quite computationally intensive, especially if you're looking at, as I said, unlike, let's say, protein folding at home, you're looking at one protein. Here you'd be looking in the direction of a collection of molecules and a collection of surfaces. And so this is now normally not a simple problem to compartmentalize and give various bits of the task, because one region of the part that you're simulating will interact with another region, right? You're not just looking at something to see how a protein can fold in on itself, not interacting with anything. You're looking at how maybe a protein would interact with other proteins. And so for this type of computing, the people who've designed the software had to think, okay, how do we want to solve smaller portions of the hard problem and then iterate a solution? And they use MPI in this case to essentially distribute portions of the region that they're simulating. And they require communication, right? In this case, a portion of the, let's say, volume that they're simulating will interact with another volume, the other portions of the volume. If you took a volume and split it up into 8 sub-volumes, they're not independent. So you have to communicate, and you have to use essentially a fast communication. And normally you want to use a fast machine. You could normally try to push this to the internet, but it would be waiting a while. And you really have to have this fast communication in an HPC setup. And an example of this is a particular modeling that they've done to see how well this particular bit of software scales. And they were looking at essentially just a carbon atom and looking at its heat of formation. So looking at this molecule, the carbon atom molecule, to see how well they do this problem, right? So here the issue is it's a real world problem, and you can't go to infinite CPUs and get an infinitesimal amount of time. So they started off with a problem where you break it up into spatially. So it's essentially a region where you break it up into several different domains, and each computer is given the task of solving a portion of that domain and then interacting and communicating its results to the neighboring computers, neighboring domains, and then get that communication back and forward. Right, so that's the process. They're trying to, this is how it goes about trying to solve a hard problem. And you can look at just an example here where even using 128 cores, so that's quite a lot of computing resources if you compare it to a workstation, right? Your laptop, your workstation might have 8, maybe it has a bit more, right? It still took the first set, it took 11 hours to do this simulation, right? So that's quite a bit of wall time. If you were sitting there and hitting enter and then just waiting on your workstation, that's quite a long time to wait to get an answer, because you probably have to wait a lot longer than 11 hours. But as you increase the computing resources, right, you go from 128 to 256, the wall time shrinks. It does seem to shrink pretty good, like quite well. You increase it again, it increases, the wall time decreases again, right? So if you increase it by a factor of 2, close to 1,024 computing elements, right, cores, you get quite a good scale up. It basically now takes 1 hour. So that's a very short amount of time, right? It's fast and it's low cost. You're not using enormous amounts of resources and it's going quickly. But as you increase the amount of CPUs, you're essentially decreasing the amount of the problem that each core has to deal with, each CPU has to deal with. And there's a point of diminishing returns. Eventually, you increase it by a factor of 2 and you don't actually get like a massive reduction in the time it takes to do that computing. So if you went from 1,000 cores to 4,000 cores, you'd still be normally kind of waiting about an hour. And that's a massive increase in the amount of cost of that running that simulation. It is faster, but it is not a lot faster. And this is the reality of real world simulations and real world HPC systems. There's a point of diminishing returns where you can keep going, but you might not actually get any scaling. And at some point you have such a small problem that there's nothing to do. It's as if you took an array of 8 elements. If eventually you do 16 CPUs per 8 elements, then nothing happens, right? They're just waiting. So that's the idea. And so in kind of highlighting this is the relative cost and number of cores. So there is, in this particular example that I showed, there's a sweet spot where you have low cost, large number of cores, and you're normally getting quick wall time, right? So it doesn't take that long. If you had 1,000 cores, you have an hour, and that's great. But then as you start increasing, the amount of extra resources you need to get a small decrease in the wall time is just not worth it. So you have to weigh this up, and if you're very new to this type of software, it can be quite tricky to figure out how to do it. So this is something to think about. It's just something that you'll have to eventually start thinking about when you start really doing these large projects and trying to improve your science. I'll skip this little bit. I mean, it's just looking at sort of what the distribution is for jobs running and where the sweet spot is, but some problems can really scale to tens of thousands of cores, and other ones are like, well, normally what we want to do, that size of problem is good at 100 cores, so we do lots of them, right? So you may want lots of jobs at 100 cores, and maybe another group will say, well, actually, we need to do one job at 20,000 cores, right? Using enormous amounts of resources, but to do once. Whereas you might be saying, well, we need to do lots. And so there's a give and take that you have to do. And there's something that is completely dependent on the problem you're trying to solve. So something to really think about, what is it that you're trying to do? And the goal, of course, of this particular subsection is to get an idea of how do you increase the scope of your science, right? If you're given extra computing resources, could you increase the scope of your science? Could you do better science, high resolution, more complex science, right? Because some, and this is true of actually a lot of computational workloads, algorithms and so on, can do better if you give them more computing resources. up to a certain limit of the actual problem, right? So you can parallelize your codes to try to make use of this extra computing, right? And the subtle thing, of course, is that the parallel portions, of the workload, how much they actually do, and how much is just spent parallelizing can be a bit tricky, and it can expand faster when the problem starts to scale up. But the idea is to tackle larger problems with more cores and the same amount of all time and do better science. And for everybody who's kind of, just have a think about what is the problem you're trying to solve? How big is it, right? If you were doing something that is normally, let's say, has millions, billions of elements in the computing regime you're looking at, maybe you can do lots and lots of CPUs and do one. Maybe you're like, well, actually, we need to run 50 different types of these simulations. So you want to make sure that you take maybe a little longer, but you can run all of them, right? And that's the idea of increasing the scope of the science. So how do you start doing this type of exploration in case you've never done this before, right? If you have existing software, or even if you're developing software, play with your workstation, right? Start off with like saying that, well, I want to go to a supercomputer, let's treat it as if a workstation with, I just ask for one node and I don't necessarily worry about details of other nodes. I just try to see what happens as I increase the computing resources on one node. I just look at the wall time, how efficient it is, maybe where my bottlenecks are. And then you move to thinking about maybe larger problems that require communication between nodes, this MPI, using MPI. And in that case, you might say, well, I'm going to try now 2 nodes with lots of resources and see what the impact is on wall time is, what the efficiency is. Start off small and slowly build to something bigger. And start off with a known problem, right? So something that's simple that takes, I don't know, 2 hours to do on your workstation, and just see how it starts to scale. And then you can see how your algorithm scales and how the software scales. Or if it's existing software, use the resources that are available to you to see how that algorithm seems to scale, and try testing those problems as well. Now we just say, the simplest thing is just quickly plot up wall time versus computing time, and you can obviously calculate cost and see where the sweet spot is for running your simulations, essentially doing the analysis you want to do. Now, in part, obviously that may seem daunting task, especially if you're new and you haven't thought of like, okay, how do I even begin to do some real world like supercomputing? But there are lots of resources, right? So there's lots of documentation on Pawsey. We do our best to help out. So there's documentation, there's of just how to use the system, of course, right? How to use modules, what resources are on what systems. There's a decent amount of knowledge base of submitting jobs, of trying to figure out, best policy and so on. So there's sorts of documentation first, of course, if you have any questions, but you can also get assistance, right? So we obviously run support. You can open up a ticket and ask for some help. But when doing this, right, remember, these are real world problems of a code base that's complex. You may be doing software that end up a particular problem that's maybe hard and complex, and we don't have all the information. So it's very useful to say, we did this with this much resources. This is the error message we got. This is where the files are located. This is the ID. Normally, these are the problems we're kind of having, right? Quite a bit of detail is useful if we're really going to try to help you kind of go to the real world case. And just as a point, of course, if you have login issues, you can contact this, but never tell anybody your password, right? It goes without saying, but it's good to say it again. You can ask for some login assistance as well. Now, there's also an Ask Me Anything session run by Pawsey. That's really good if you have maybe more complex things that you'd want to tackle, or you really want to kind of see what other people are tackling. So it's an opportunity, the Ask Me Anything sessions. You can look and find them. You can sign up and register and see what kind of propose what you would like to discuss, but you can see the discussions that other people are going to have, and you can talk to us, right? We can kind of work through maybe a far harder problem than, or at least maybe help you think about how to deal with a hard problem, right? Maybe whether that requires actually looking at your code and developing it some more, making use of resources that otherwise wouldn't be there. If you have a bit of software that never uses GPUs, but you wouldn't like to use GPUs, maybe this is a good point of discussing it, right? Saying, listen, I'd really like to see what people say, and you can ask some experts, right? And you can use this knowledge base of peers asking questions, and also experts answering questions to your advantage. And I think that's a really good point of getting assistance for real world problems, looking at other real world use cases. So yes, please make use of this. And I think I will open up to actually any questions right now. So we can ask us anything.
You can increase the volume of the
A mini
speakers.
Ask Me Anything. So give you a minute to put your questions in the chat in case you have any. Okay, could you recommend some books or articles about parallelism?
Okay, let me. So oops, there's. Just make sure that I'm. So we don't get an echo. Oop, that's fine. There's lots of online resources. There's a few that we've listed here for parallelism. I can send some specific resources that kind of introduction to parallel computing. There's quite a lot online. I can't necessarily recommend anything specific because some of them are very tailored to a particular type of parallelism, kind of thinking about a particular type of problem. That's usually the easiest way to kind of do these type of tutorials where you're like, okay, this is an issue and this is what we want to do and this is how you parallelize. For example, OpenMP thread parallelization is very different from MPI parallelization. The way you would try to start thinking about how you'd have to do stuff is quite different because one doesn't necessarily require you to think about how do you split up the problem and have things communicate in a complex fashion, and the other one doesn't. What we can do maybe is, as I said, is give a larger list of links and bits of information. Book-wise, I can't think of any particular book I've read, and most of the stuff I look at is online. You'd be surprised what's on even stuff like Stack Overflow of just like, how do I parallelize a problem? But there's other links we can maybe provide a little later.
Okay, so what we can do is we will be providing a link to the PowerPoint, and we will also be providing you with the recording when it is available. We can provide that list of parallel links to you at that time. All right, so I have a question as well. How resources at Pawsey couple with code internals that are meant to use GPUs, specifically thinking about the Julia language, where quite a bit of their functions are meant to be run in the GPU.
So for Julia and other similar languages, normally the language has a code to check what's available in terms of resources. So it will do its best to actually try to offload to GPUs if there's GPU infrastructure available. And not all systems have GPUs at Pawsey, and that's true kind of everywhere. But you need to make sure that you are saying that I want GPUs and choose an appropriate system. So there's, I don't know how many nodes on Zeus have GPUs.
There are eight nodes with 4 GPUs each.
Yeah.
I think so, the P100.
Yeah, okay, that's right.
And some other GPUs, older GPUs, yeah.
I think all the GPUs are in the same partition though, even the older ones, right?
There is a GPU queue partition.
Yeah, exactly. So,
dedicated.
but that, as far as I know, the GPU queue doesn't necessarily specify just the newer GPUs. It just specifies all the nodes.
Yeah, all the nodes.
Yeah.
You can have constraints on which kind of GPUs you want to use.
Yeah, you have to put extra constraints. But in terms of that case, right? If you are explicitly asking for the GPU queue and running on that queue, the languages such as Julia and other ones which have hooks to essentially pull a resource and see that they have, if their GPU is available, to then essentially access that, then they'll make use of that. For other languages, I mean, for other particular code bases, it depends. Some code bases, you know, when you compile them, they'll be like, okay, these are the resources available. I'll try to make use of them. These are the, you know, let's say for NVIDIA, for CUDA, right, which is obviously a way of kind of doing parallel GPU programming. If that's present, those codes will try to then use that, and then once if they're on the appropriate node, they'll make use of the GPU resources. But it depends, particularly on your code base that you're looking at.
All right, just unmuting myself there. All right, what we'll do is we will be distributing the recording when it's available. We will also be distributing the PowerPoint. I'll also link you to the first recording, which has some of the other things that are being asked in the chat around submitting a job on a CPU, etc. At this point, I'd like to thank you for joining us for today's session. I'd like to thank our presenters, Christian and Pascal. Also like to thank our facilitators in the chat, Basha and Alexis. If you are interested in future sessions, Pascal mentioned the Ask Me Anything, which is a series of every Monday morning. It is happening at 10 o'clock to 11 o'clock Australian Western Standard Time. You can register for that on pawsey.org.au/events. Other than that, we hope to see you at a future training session, and thank you again for your time.